All right. Hi, everybody. It's my great pleasure to introduce our speaker today, Ricky Chen from Meta Fundamental AI Research. So Ricky is a leader in the intersection of machine learning and dynamic systems. So previously he published a very influential work called Neural ODE. Some of you probably play with that to some extent. And recently, he's one of the main contributors for emerging new deep generative framework called flow matching, and which is gradually replacing diffusion models. Actually, the most recent one, stable diffusers, I think they're using flow matching mostly, and it's very powerful and beautiful because of it's very generalized, unified view of generative models. So I think Ricky is going to tell us more about it. Ricky, go ahead.
Thanks for the introduction. Okay, Okay, great. The echo's gone. Yeah, thanks for the introduction. So I'm here to talk about the flow matching recipe for general modeling from continuous to discrete. The main sort of theme of the talk is we're going to be talking about the very basic flow matching algorithm, but try to extend from it a generalized recipe that we can then extend to different domains, including discrete domains as well. And we'll see that what underlies flow matching is actually a very simple recipe that is extremely modular, and we can basically replace certain pieces of it with different components. And if you sort of choose different certain choices for these little sub-modular pieces, then you get existing models like the most basic flow matching or diffusion models and the like. So the slides that I'm using today are adapted from this flow matching tutorial with Yaron Lippman and Heli Benhamu at NeurIPS last year. So a lot of credit to them for the slides. Hold on. Okay. And this talk is centered around this flow matching guide and code that we released at the end of last year as well. Basically, you have a little bit of a summary of all the flow matching works and extensions in a single archive paper, as well as a bunch of code examples for training images, both continuous and discrete, as well as text examples in this flow matching GitHub repo. So you can take a look at the guide and also at the codebook, the code base if you want. The slides for this talk are mainly following the guide and code. Okay. So flow matching has been used at scale for quite a few different applications. It's quite a simple algorithm, and the main version that people know of are the ones that for generating continuous data, right? So we can generate conditional text, generate video or audio, and we can also generate text to image. People have also done this for AI for science, where there's a lot of constraints or symmetries that you want your model samples to satisfy, or to maybe lie on some Riemannian manifold. There's some sort of geometric data. People also apply this to action models for manipulating robots. One thing about the talk maybe is if you have any clarification questions during the talk, feel free to just ask, especially if there are clarification questions, if something doesn't make sense. All right, so what is flow matching? To me, flow matching is an algorithm, a very scalable algorithm to train dynamic general models, in the sense that we want to learn a stochastic process that follows some dynamical system, and it's aimed at generating some particular data set that we train it on. And how it works is we basically regress something that we call a velocity. And the velocity is just something that points a particle or the current sample towards the data distribution. And so we sample by following this velocity, and then so when we arrive at a particular time point, we'll arrive at the model's distribution output that is supposed to be mimicking the data distribution. Okay. So the general modeling problem looks like this. This is just, imagine this is some RD space, it's continuous space. We have a sample from a really simple distribution, this P distribution, and we have samples from Q, which is our target distribution that we want to fit to. And the idea is that we want to go from P to Q in a way that we can somehow transport the samples from this really simple noisy this Gaussian distribution to samples from this Q distribution in a way that we can say we are creating IID samples from this target distribution. And the simplest way is to just learn a map between x0 and x1. We say x0 is from the noise, x1 is from the data, right? Now, if we want to learn a direct map, this is probably the most maybe efficient way of generating data, but it's not very easy to train. This is sort of you get a GAN approach for generative adversarial networks, or you get normalizing flows. There's a lot of different ways for training such a map, but none of them are really stable in a sense. They require some adversarial loss, or they require some very special architectures. Um, and the like. Yeah. So instead of learning just a single map, just a one-step map, we're going to learn a continuous time markup process where we break down this projection between or this mapping between the noise and the data into little segments, little chunks, right? And so we have a map that says, okay, given some time t, and we'll define t later on, but it's going to be some interpolation between the noise distribution and data distribution. We'll have a bunch of very small steps, right? Some incremental steps that will slowly change the distribution from xt to some xt plus h, and so on and so forth, between time 0 and time 1, right? And the main question then is, how do we come up with all these little infinitesimal steps, right? There's a lot of different ways of coming up with this. You can get a diffusion model, you get a flow model. There's a lot of different ways that we can model. Well, there's a lot of different continuous time marker processes that we can use in order to create our general model, right? It could just be an ODE, just deterministic, or diffusion, or even it does jumps in the sense that it stays at a certain state for a very long time until some arbitrary time later on where it jumps to a different state. Right? But in general, the way we're going to go about creating the general model itself is first by thinking about the probability path. That is, we first create this this time-dependent P that interpolates between the noise and the data distribution. It's just some interpolation. This PT, this probability path as we call it, doesn't include information about um, uh, the dependencies between different steps. All it is just at a certain time marginal, right? For a fixed t, there's some particular distribution that we would like the samples to follow. And so we can create this p in a way that maybe makes sense. But by following this p, we can say there's a lot of different stochastic processes that all follow the same time marginals of this probability path. It doesn't define a joint distribution between x0, x1, or any of the intermediate values. It's only the time marginals. Okay? And there's a lot of different choices, like I said, for the stochastic process itself. For now, we're going to focus on flows. That's sort of where we started flow matching. The main idea was that at the time we thought this was just simpler. We didn't really need to add noise during sampling. We just have a deterministic function, except it's not one step. It's just we apply some deterministic transformation in an incremental step. In practice, the flow parameterization does allow faster sampling because we don't need to add intermediate noise. It's just one direct map from x0 to x1. That one deterministic path. And the flow also allows us to compute likelihoods for the model samples that we get. And it just tends to be easier and more flexible to train. There's a more general family, including diffusion processes and also jump processes that I'll get into in the end. The jumps are more related to discrete things, but we can also use it in the continuous space. These allow a larger design space. We can, we can instead of transporting only locally or even deterministically, we can add noise, right? We could also then jump to some other place that is not, some local perturbation. Effectively, what the diffusion is doing that people use in practice is they're basically they're adding Langevin dynamics to the flow itself. So they're adding something that essentially is, let's say, fix the time, and then I'm going to keep updating my sample. I'm going to add some noise to my sample and correct it so that it sort of stays at the same distribution. And the flow itself is meant to be transporting between different time values. So this is why if you really want an efficient sample, you sort of get rid of that stationary component, which is only just adding noise, but it doesn't advance your samples to the next time, PT. Instead, just work with the flow because that's the part that actually advances your sample to the next PT. Okay, so flow is a general model. Sort of here's the, I guess, one slight intuition for how it looks. Suppose we have some data distribution, some noise distribution that we showed here, and we want to map it to some data distribution or model distribution. We can think about this phi t as a warping function, right? This is not a one step, this is a time-dependent warping, being that it's given the noise, and then we transport it to some space. And the idea is that this warping function basically it's a diffeomorphism. It's something that like slowly, smoothly changes the space and its underlying samples. Right. One assumption that we do make is that whatever process we want to learn, it's Markov in the sense that xt plus h only depends on xt and doesn't depend on the history of that function. And so that means we can then write it as this warping function. Now, if we had such a warping function, this flow essentially, then in order to compute the velocity, which is the direction of where each particle should be going, if I have a particle at time t and it's at some location, it should be following these arrows, right? These blue arrows. So first we had a flow that's taking in the noise and then sort of transporting it along some time-dependent trajectory. And now if we differentiate that with respect to t, we get a velocity that says, okay, given a point I don't know if you can see the equation. Maybe move it down here. Okay. Given a transported point, this phi t of x, here the velocity will tell it which direction should this point go in, right? And so in order to get the velocity, it's very easy. It's to just differentiate. But if we only have the velocity and we want the flow, we then need to solve this ODE, kind of like doing gradient descent. Okay, oops. But the main point here is that as we'll get to, velocities are sort of a linear construct. We can do linear combinations of velocities and you get classifier-free guidance. We can do simple L2 regression on the velocities, but we cannot do that on the flow directly because the flow is something that's non-linear. It's not something that you can easily combine with different things or easily create a regression objective to fit. Now we'll sort of sweep a lot of the technical details under the rug as like how the stochastic process, this velocity affects the density itself, and we'll just use one word to sort of summarize what we mean by we want to find a velocity. We say that the velocity ut, which is the function of the particles, something that outputs a direction. We say generates some probability path pt. If I were to flow under this velocity, then the particles will follow this time-dependent density as it transports, across time. Basically, this means that the velocity ut and pt should follow something called the continuity equation, or the Fokker-Planck equation, or the Kolmogorov-Ford equation. There's a lot of different words for this, but essentially, this ut and pt needs to be coupled in no way, right? It's this ut generates a particular probability path. Okay, so then we'll talk about how do we train such a model, right? We want to learn a UT that transports from the noise to the data distribution. First is how to train it, and how do we sample from it. We're gonna talk about this in the opposite direction because sampling is much easier, and I think it's already been hinted at. But if you have a sample from the noise distribution, and we want to solve this ODE that's parameterized by a neural network, right? This UT is now is going to be learned as a flow model. Then we basically just want to solve an ODE, and the simplest method is Euler's method. So this is kind of like doing gradient descent. You at a certain point, you evaluate the direction you want to go in, and you take a small finite step size h, and you keep advancing time until you reach time 1, and that's the sample that you would get. Okay. All right. Now the fun part is how to train this. Before I talk about the general recipe, here's the main sort of simplest version of flow matching that I think you might have come across and that everyone sort of talks about. which is just doing a linear interpolation. So if we were to take random pairs of x0 and x1 during training, right? So we just randomly sample from the data distribution and then randomly sample noise. And all we do is we take a linear interpolation between the x0 and x1, randomly sample time. And we're going to just say, given this xt, which is an interpolation of x0 and x1, compute the velocity and regress it onto this direction that moves towards x1, right? So we regress it onto x1 minus x0. This is sort of the simplest version of flow matching, and this is what most people would refer to as flow matching, sort of from a practitioner's perspective. But this has a lot of names. It sort of came up in a lot of different works, including stochastic interpolants, rectified flow. This thing called iterative alpha deep blending as well. But yeah, it's a very simple recipe, and it's something that you can easily just code up in a few lines in Python, right? So we sample x1, we sample x0, we sample a random time t, we compute xt. The derivative of xt is x1 minus x0, and then we just say the loss function is we have some loss function that regresses the flow evaluated at xt to x1 minus x0, and that's it, right? So after training, then we can plug it into that Euler's method to sample from the current model. That is, we sample from sample random x0 and then just transport it according to the learned flow. Um, all right. So one thing that I didn't really talk about is how do we get the um, right. So one thing first is that we don't actually need a Gaussian as a noise, right? It could be any noise distribution, could be any distribution, could even be a data distribution. Right? We might want to go from like an image of cats to image of dogs or something like that. Um, and the second thing is we don't actually need to independently sample the x0 and x1. They could be sampled from some arbitrary joint distribution, which is what we're calling a coupling. A coupling is just a joint distribution between x0 and x1. And all of them will satisfy the property that once you train a model to the optimum, that UT will be a UT that generates the probability path such that at time zero it's x0 it's p, and at time one it's q. Okay. There's going to be some probability path that interpolates between the different distributions, and we can use a different coupling. We can use any two different distributions, and the model will just learn a transport between the two different distributions. Um, It doesn't, for example, one thing is it doesn't, we don't preserve the joint distribution. We don't preserve the coupling that is being used for training, right? All we're saying is that this UT will transport samples in the sense that it'll learn the right time dependent, time marginal distributions, but it doesn't necessarily preserve the correct joint distribution that you use for training. In fact, it'll actually be more efficient, which I'll get into later. You can use an independent coupling, right, and learn a model that is more efficient, has a better pairing between x0 and x1 than the random coupling that you use for training, or any coupling that you use for training. Actually, it'll always improve. Um, right. So yeah. So the main basic recipe is just let's just somehow we'll get into why this actually works in the next slide. All right, so let's think about try to get to the general recipe here. So let's think about generating just a single data point where we want to basically somehow transport or the noise distribution into just that single data point, that a direct distribution centered around x1, right? And so we can just think about xt or this flow as a conditional flow, condition x1, and this is something that looks like this. And so given this flow, this is very simple, right? It's just concentrating the Gaussian to be very, very small at a center point. And it's a very simple interpolation. Let's take this conditional probability path. Uh, sorry, here, conditional probability is p of t given 1 of x given x1. And we'll average it. We'll marginalize it, right? We'll take an expectation of this over x1, where x1 is coming from the data distribution. And now this PT is a path that interpolates between the noise and the data distribution that we have, right? This is sort of like just saying that at time t, right, this is kind of like a Gaussian mixture model, right? It's a way of marginalizing out the data distribution. And so you get this marginal probability path. Now, the nice thing is if we were to take the conditional velocity, which is these blue arrows here, they all point towards x1. It's very, very simple. It's all pointing towards x1 with some magnitude that's predetermined. And we also take an average, right? But here, this is a conditional average. We condition on xt, x, right? And we marginalize out x1, right? So given during training, given that we took random samples of x0 and x1, right? We randomly passed through some of these xt values. And so there's a dependency between xt and x1, right? That's what this expectation is over. Given the xt, we try to predict or infer which of the data points were passing through this particular value of x. And we just average this expectation of the conditional velocity, right? And this will get us the blue arrows here on the left, on the top left. These blue arrows is the one that's going to be generating the marginal probability path, right? So this is something we call the marginal velocity. It doesn't depend on x1 anymore. It's the thing that we want to learn, and it's going to be transporting from the distribution at time 0 to the distribution at time 1. Okay. So we wrote this as sort of like a theorem, but it's quite easy to prove if you go through the continuity equation. Basically, we just say that the marginal velocity, as we defined it on the previous slides, generates the marginal probability path, as we defined it on the previous slide. And so the idea is then for flow matching is we just want to regress onto this marginal velocity. Right? The marginal velocity is intractable because we don't have access to it, but it is just a conditional expectation of the conditional velocity. And so we can actually just regress only onto the conditional velocity because the optimal solution of this regression problem is going to be the conditional expectation, right? So we just wrote this also as a theorem in the original flow matching paper, just saying that the gradient of the flow matching loss, which regresses onto just the marginal one, is intractable, but it's equal to the gradient of the conditional flow matching loss. And this is what people typically call the flow matching loss now. Yeah. Is there any questions up to this point? Were things clear? All right. So go back a little bit. So one question that we usually get is, can we use a different norm here, right? So can we, instead of the L2 norm, use like a L1, L infinity, or like some sort of like L pips loss, like some loss that sort of makes that people tend to like better when doing image reconstruction? The answer theoretically is no, because then it doesn't necessarily, if you just replace it with the L1 loss, for example, it doesn't regress onto the optimal solution. It's not the conditional expectation. But there is a family of losses that we can think about that it's both sufficient and necessary for being able to say this statement that the gradient of the two losses are the same, right? If we just plug in the marginal velocity versus plugging in the conditional velocity, that they still get the same expectation, at the same gradient in expectation. And that family of losses is exactly the Bregman divergence family. So a Bregman divergence is if you take a convex function phi and you write it down sort of this way. If you plug in the L2 norm for phi, you get the L2 norm that we saw in the previous slide. But you can also plug in, for example, the L1 norm for phi as well. You get a different expression. It's not the same as just on the previous slide replacing the 2 with a 1. But this is a family of losses that is sort of both sufficient and necessary for being able to say that we want to regress onto the conditional expectation that we eventually want to learn. So this Bregman divergence, it's also quite strong. It's not something we've really shown to be really that interesting just yet, but I think in this year or in the future, we'll see that this is quite flexible and really helps us generalize to different stochastic processes and different ways of training beyond just the L2 norm, but while also staying theoretically sound as well. Okay.
Ricky, I have a quick question about the previous slide.
Yeah.
What happens if you're not equivalent? I mean, I know that this is to guarantee that the gradients are equivalent.
Mhm.
But I only care about the second one. I mean, even if
Yeah,
does that work?
so I think the main thing we want to care about is that the two have the same optimal solution, right? So that if we were to use the conditional flow matching loss, we can then say that at the optimal solution, if I were to try to optimize it as best as I can, I should recover the marginal velocity. So that's the condition that we really want. This is a stronger condition, right? This is, as I said, this is saying at every single point we have in the gradient being the same in expectation. So you're right, this is not necessary, right? But it is nice to have because now we can say that we're basically, it's like doing stochastic gradient descent, but on the flow matching loss itself, where we just directly regress onto the marginal velocity, which is the thing that we want to recover in the end.
So have people tried things that are beyond the Bragg divergence, where it's known to be non-equivalent?
I think so. I think people have tried different losses, different norms. I don't know if they've caught on because I don't think people have seen the huge difference. Any differences I think would be due to like, some sort of bias or like, the test metric maybe be a little bit better. But yeah, I personally don't use it. I haven't seen like a huge success story of using a different loss other than just the L2 loss.
Okay,
Yeah,
thanks.
yeah, no worries. Any other questions?
Go ahead.
Okay. All right. So then the question is, instead of doing just the linear one, or sorry, like just let's following the recipe, right? So following the recipe, we sort of constructed a way to transport the entire noise distribution to a single data point. And the question is, how do we choose it? Here's a little quick note on why we chose the linear one in the first place, the one that just goes in a straight line. But essentially, if we wanted to minimize the kinetic energy, which is this term on the left, that is, if we were to sample from the marginal probability path and try to minimize the expectation of the norm of the velocity, this sort of translates to like a minimum work, sort of like a minimum cost transport plan. Then we can upper bound this by randomly sampling pairs from the coupling from x0 and x1 and trying to reduce the kinetic energy of the conditional flow itself, right? So this is a very simple bound, it's a very loose bound, but it's one way of trying to say, okay, why do we want to go in a straight line is, think about just having your data set's just one data point, right? Then kind of obviously you want to go in a straight line. Um, yeah, so this is sort of the path that we use in practice. It's just going a straight line. We can sort of say that it is minimizing a bound, but this is not a tight bound. And because it's not a tight bound, it's not optimal transport, right? It will be tight if we can also optimize the coupling. That's the key point. But it is also something that works very well in high dimensions without even thinking about optimal transport. So um, here's an experiment we did. It's just some two-dimensional distribution with noise added to it, such that the noise is in like 10,000 dimensions. Um, but you can see that the learned model on the left, when it's only 2 dimensions, it sort of needs to sort of warp around, right? And in 100 dimension, it's also still curves, but in 10,000 dimension, it's now just a straight line and with very little curving. So this is because in high dimensions, you can just take random pairs and do linear interpolations, and there's not too much um, collision going on that really affects that you need to sort of uh, like deviate from the straight path. Right. And then the bottom one is if you were to use a cosine scheduler, which is what people sometimes also use, you can see at 10,000 dimensions, it's not as straight as the linear one. And so this is, I think, one of the reasons why we see that the linear or the Kondo T-path does scale better than like a diffusion model or a different scheduler, and why people are sort of preferring to just use straight paths now. It seems so simple, but it's just because it works better in high dimensions. It scales faster. Okay, so back to the general recipe. One thing we can think about are affine paths. That is, instead of just going in a straight path, like with a linear, with a constant velocity, we can think about just a family of affine paths, which is just a combination of x0 and x1. Right? And in this family, we can convert the velocity to the expectation over x0 or the expectation over x1. And both of these sort of have names that appear in the diffusion literature, which I'll get into just in just a bit. But one thing to note is that if we were to convert from the x0 prediction or the x1 prediction to the velocity, then singularities appear because these coefficients, they go to zero or they go to infinity at certain values of time. Just think about if if you had a model that only predicts x1, right, and your time is very, very close to 1, then the velocity, if you're not exactly at the predicted x1, then you need to basically go there in an instantaneously fast way. So the velocity blows up if you were to convert from x1 prediction to the velocity. Right? So if we further make the assumption that we have an independent coupling during training and the noise distribution is a Gaussian, right? So like I said, the time zero distribution didn't have to be a Gaussian. You can still convert between all of those as long as you have an affine coupling. But if we also restrict ourselves to the Gaussian path, this is where we get the sort of the connection to diffusion models and the probability flow ODE, where they call these the X1 prediction or the X prediction, the denoiser, or the noise prediction models. Right. So in our guide, we have a little table that says, okay, here's how all the ways of you can combine, so you can convert between different things. You can convert between x1 prediction to velocity, and all of these sort of you can see there's a division, right? There's a division by sigma t or alpha t. One of them is going to be zero at one of the endpoints, and so there's always some sort of singularity happening. And the score function only makes sense when you have a Gaussian path. So when your noise is Gaussian. The other ones, the affine ones, you can still convert between the two. Uh, like if you do like image to image translation or anything that's not just noise to image. Yeah, so a quick summary slide. So for flow matching, the recipe is a little bit different from how we create diffusion models, right? So diffusion models, even if you convert to the deterministic case in the end, what they typically do is you would define a forward process that adds noise to data, right? So there's some sort of sequential process that adds noise, and you want to reverse it. And sort of there's a bunch of different combinations of like how to do we marginalize first and then we reverse, or do you reverse first and then marginalize? But in the case where you reverse first and just throw away the forward process, you just think about the reverse process that goes from noise to data and then marginalize it. That's basically flow matching. So flow matching, I think in one way of thinking about it is it sort of gets rid of a lot of the unnecessary components that diffusion models sort of created when they first constructed their construction. And in particular, we see that as long as we have this p t given 1, this way of like defining some conditional probability path, we don't really need to think about any sort of stationary for process. We don't need to think about Bayes rule to reverse anything. And we typically, there's less of we call this a signal to noise issue problem, which is if you have a stationary forward process, you technically can only reach the full noise, the Gaussian, at time infinity, right? But people always truncate. So there's a lot of truncation errors happening for diffusion models that flow models sort of just get away with, get around with. So anyway, yeah, there's a lot of small details in the construction, even for the pure continuous case, for the deterministic case. But I do think that the recipe on the left is a lot more general, and we'll see that it's to me it's a lot more modular and easier to work with. Even for the simple case of like these linears, but like I think from a research perspective, we can also think about like having a toy where all these little components we can mix and match, and eventually generalize to something that's non-Euclidean, non-continuous. Yeah, so I think the main takeaway here is just if you do the linear thing, it is something that works really well at scale. This has been tested by both by us by theory, but also by people doing the actual scaling. Like I said, when we did like movie gen, we tried to generate very high resolution videos and audio. We did a lot of human evaluation metrics between diffusion models with different schedulers and flow matching the most simplest case. And flow matching basically always won out just because it scaled better. And one idea for why maybe that happens is that plot that I showed earlier, which is we only went to 10,000 dimensions and we saw that the paths were always straight. and this meant it's easier to train, and there was no collision happening. There was no marginalization that really needed to be done. Um, okay. Any questions regarding this first part of the talk? Oh, um, sounds good. So in the interest of time, I'm gonna skip over the Riemannian version. Uh, but the main takeaway here is that we can define Riemannian manifolds. If you're familiar with this, you would know it. If not, then maybe it's a bit too complicated. But basically, like for example, if you take a sphere and you take a point on the sphere, we can still define vector fields on the surface of a sphere, and everything basically holds from the continuous case. The main thing that benefits flow matching is like especially for diffusion is diffusion processes. You have to do a random walk in order to add noise to some sort of data point. But for flows, we just directly learn some sort of interpolation between 2 points, and we can just use the geodesic interpolant for this, right? So it's something that's simulation free, and this is something that scales a lot better than diffusion models for non-Euclidean spaces. There are particular very special Euclidean spaces, Riemannian manifolds that diffusion models do work well in. But in general, if you want to work with general manifolds, um, flow matching is sort of the way to go about it. I'm going to skip the details here, but maybe show you just a quick application example if you're interested in sort of modeling geometric data or like on manifolds or sort of with equivariance and things like that. Feel free to take a look offline. But here's like on the right, so uh, here's just a 3D mesh. So it's made out of little triangles to define a surface, and we have a distribution that's warping a uniform distribution to some target distribution on the mesh. It's just a cool way of just like modeling meshes. So for example, if we wanted to model something that's on the surface of the Earth, right? We don't really want to be modeling as a perfect sphere. We want to model all the bumps and all the oceans, perhaps. And now we have a much more complicated surface to work with. But yeah, so like, if we want to do any sort of like general manifolds, we also have works on doing this for materials. So materials is sort of it's like a crystal where you don't have a finite number of atoms, but you have infinite number of them. What we do is instead we model what we call unit cell with periodic boundary conditions. And so, this cell sort of like tiles in every single direction. But all we need to do is model the points in this cell. The key point here is that we need to model, it's not Euclidean because if a point leaves one of the edges, it warps around. It's like Pac-Man, right? It warps around to the other side. At least the representation does, right? And so we need to take that into account. We have a different way of defining geometric path, and there's no Gaussian distribution anymore, right? Because it's a constrained space. And so there's a lot of differences compared to the Euclidean, but also the same recipe holds. We just need some way of going from the noise, which is the uniform distribution over this unit cell, to a single data point, and then we regress onto that velocity, and that's it. Um, yeah. So here's an interesting. Is I'm getting to the discrete very very soon. But I also talked about diffusions and jumps and sort of there's a lot of different continuous time Markov processes that we can work with. And they're all kind of, once you discretize them, you can think about this transition kernel saying, given some sample at xt, how do I sample my next time point, my next t plus h, right? So for flows, that was deterministic. For diffusion, it's like, it's some Gaussian if h is small. For jumps, it's kind of like it's like a mixture model. And basically, there's a transition kernel for Markov processes. And in this work, what we did for generator matching is to try to generalize this recipe as general as possible to Felder processes. But anyway, so to our arbitrary Markov processes uh, contingent to some class. But basically, the general idea is sort of you can write this transition kernel the t plus h given t given some sample at time t as just a distribution centered around x plus a little offset. This offset is what we call the generator. This is the infinitesimal generator. And there's a little bit of error that we don't really account for because once we take h to 0, it doesn't disappears once we go contiguous time. All right, so this thing is basically what the velocity in the previous in the flows was representing. This is what we call the generator. It's technically an operator. I'm gonna skip this as well and just talk about the discrete in a sense. Yeah, so for sampling, it's also very simple, right? So you for given xt, given some direct distribution at xt, and we add some h times this generator this offset basically. It changes the distribution, and then we resample from this distribution. This part makes, I think, to me, makes a lot more sense when it's just a discrete state space. So we're gonna move that there. But the general recipe still holds. Basically, the Kolmogorov equation takes into account flows, diffusion, jumps, and sort of arbitrary combinations of these things. So you can like jump diffusion models. And the same recipe holds in that we want to maybe design some probability path. It could be implicit. It's not always explicit. But essentially, we want to design some conditional generator that generates a single data point, right? Here, the example on the right is just it always does jumps instead of like a continuous local movement, sort of infinitesimal movement process. And we want to average the generator itself. Then this averaged generator, this marginalized generator, will be the generator for the probability path, for the marginal probability path, right? In the sense that they would still satisfy the Kolmogorov equation. And for this, we would train using any Brakmann divergence, including maybe just the L2 norm, but there's better choices than the L2 norm for different classes. All right, so let's talk about the discrete. So for discrete, what is discrete? It's a state space. We're still going to have a continuous time model, just because that tends to be easier. It's easier to create to take a limit, right, as h goes to 0. But now we have a discrete state space, and the way that we represent this is that we have sort of for language models, for example, we have vocabulary size, and we have d of these variables. So t is just some discrete space, and then yeah, it's high dimensions in d number of dimensions. And this is what the generator will what the generator framework will look like for the discrete case, where we have a direct distribution at x and y. And this is saying, what is the probability of going from x to y, right? For first, give it some infinitesimal time. And it's going to be equal to some direct distribution. This is a PM, there's like a one hot, right? Plus h times this offset. And one thing you might notice is that this offset will always sum to 0, because that's what ensures, so if you sum over y, it should be equal to 0, because that's what ensures this right-hand side is a valid PMF. You can think about this right side as basically like taking the simplex and starting from a single vertex of that simplex, and we move towards the middle of the simplex, the interior, right, by some step size h, some direction u, and then we resample our next xt. We sample from this. So just an example of like what a discrete space or discrete flow matching can do. For language modeling, what we typically have is the vocabulary size. This is the number of tokens is around usually 50,000 or 100,000 now, and the sequence length is typically 1,000 to much higher than this. So this is, I think, on the smaller side. But we can basically say let's generate text, right? So let's condition on the doc string and generate the code that would return that doc string and maybe pass some unit tests. Now, one way to model this is to try to model the entire sequence, which is just basically the entire state space, which is basically intractable. So we don't really want to be going from sequence to sequence. So our x is not, if x is a sequence, right, and then the number of neighbors that I can possibly go from x to y, right, the number of outputs here is on the order of t, or actually, it's the vocabulary size to the power of d, right? Yeah, so the general state space is not tractable. So instead, what we're going to do is we break it down into one token changes at a time. So that is, given x, I'm only going to look at the neighbors that change from x one token at a time. That's it. So it's a one token change, one token neighbor graph. So what's being visualized here is there's two variables, right? One on the x-axis, one on the y-axis, and this UT says for all, if I fix the the x-axis and I only change the y variable, then these are the possible rates for getting to the one token change graph. Or if I fix y and move along the x-axis, these are the possible rates for going along that path. So it's very analogous to the continuous case, although maybe I think people aren't very familiar with the discrete case just yet. I'm not that familiar yet. I'm still learning. But in the continuous case, right, when we had the state space being just RD, we still modeled a velocity that basically was factorized for each dimension, right? Each dimension just said, we go a certain direction in that direction, in that dimension. And now it's just instead of saying we still have condition on X, right? But our output is basically the output of all possible nearby states. That's one token change. Okay. Yeah. Oh yeah. Sorry. Yeah. So the notation we typically use is given the entire sequence, our rate is defined per dimension for one token change. Says yi would be like one value of the next like the replaced token. Okay, so for discrete states, one really simple probability path that we can work with is just mixture paths. That is, given some p, which is some noise distribution, again, like it's a uniform or a delta or like some distribution. Again, only on a single token. That's what the I means. It's not on sequences anymore, just a single token. And then we say there's a mixture path between this noise distribution and the delta distribution at time one. Again, it looks very, very similar, except it's a mixture path. And we can then do the exact same tricks as let's average the marginal probably, average the conditional probability path, average the conditional velocity. There's a little bit of art involved here, as you might have guessed. This conditional velocity, basically, we need to solve for it. We need to construct a conditional velocity that makes sense. But basically, this thing just needs to go to x1 at time one. Okay? And so it looks very similar to the continuous case in the sense that, like, when if you're not at x1, if your x is not at time at x1, at time close to 1, this thing blows up, right? And so it says I must go to x1. Yeah, so for the training, we also we can use any Bregman divergence. And here's what the sampling looks like. Remember, when I said neighbors, it's not like we don't embed it in the continuous space. It's being drawn in the 2D grid, but like the neighbors are the axes aligned neighbors. And so that's why each jump will always be along only the y-axis or the x-axis, right? And so this is what happens when xt crosses time. Xt will stay at a certain state for quite a while until it jumps to a different state, right? And on the left, you can see what this marginal probability path is looking like. Basically, it's a mixture model between the noise and the target. Okay. So for this sort of case, we applied it to code evaluation. I'll skip this, but we tried beating autoaggressive sometime last year. We didn't really succeed. It's still a little bit off. But I think we're getting closer and closer to sort of getting to the same performance as an autoaggressive model for code generation, which I think is quite exciting. But with a non-autoaggressive model that doesn't need to be generating things from left to right, but you can generate things in an arbitrary order. So for example, here we condition on some comments that we believe this algorithm should satisfy, and then we just ask the model to generate the rest. One interesting thing about this, so we talked about mixture path, and most people are playing around with the mixture path. So if you might be familiar with the mask diffusion model, that is a mixture path where the noise is just a Dirac at a very special token called the mask token. Right, it's like the 4 process they use is you have random chance of masking out a certain every single token. But I'm pretty hopeful that we can create more interesting stochastic processes as well that can generally make use of maybe similarities or semantics of the discrete space and not just only use the masking process. The masking process is sort of something that's very, very general in the sense that you can apply it to any domain and it sort of works. But if you have extra domain knowledge, it's useful to use that. So one of the works that we had from last year called this flow matching with general discrete paths is we created the velocity. This is sort of doing the automating the art part of flow matching a little bit. So if we have any conditional probability path, a condition or not, like you can imagine this conditional x1, but basically as long as we can design some probability path that like at time 1 concentrates to a one hot, right, a Dirac distribution, then a conditional velocity, ignore the connect optimal, but a velocity that generates this probability path is written like this. So all we need to do is know the time derivative of pt, and we have some form like this. This is a bit hard to parse, so just to give it an example, this is easier to look at. Let's assign a metric, some distance metric between discrete states, in the sense that d will only be will only be zero if and only if these two are the exact same state, and it's going to be positive elsewhere. So you can think about it as a, like, it's some sort of similarity metric between the different states that we can try to design. And we basically have something that looks like this. This is kind of like a Gaussian, but discretized, right? So we compute the distance to every other point, um, and then take a softmax. It's like a quantized Gaussian. It's a quantized distribution. And the UT is basically if I'm at X and I want to go to Y, then the rate of going to Y is proportional to the PT given 1 multiplied by this thing. And the interesting thing is the ReLU. So the ReLU mix is asymmetric. It means this thing is positive, right? This entire velocity is positive only when the distance between X to XT is farther away than between Y and X1. Right, so Y is closer to X1 than X. If Y is a state that basically is closer to X1 than X, the current X, then there's a chance of going towards Y. Otherwise, there's no chance of going to Y. So this is very similar to the interpolation path that I was talking about, right? So it's a way of getting closer and closer to X1, in a sense. Okay? And we applied this basically to images that are tokenized. So when people use like a VQ-VAE to try to tokenize images or a continuous domain into a discrete latent space, people like learn the latent embedding with an L2 loss with a 1-year neighbor. And so that discrete, even though it's discrete, it's like a quantized space, right? It generally has a metric associated with it, which is the Euclidean distance. And so we used that. We used a VQ-VAE to train the latent encoder, and then did ImageNet training. And basically, the thing we wanted to talk about was that you can use the mask in this case, but it doesn't outperform the autoaggressive model. And if we were to use additional information like that, we know, okay, we should impose some sort of metric because there's some sort of similarity metric, even though it's a discrete space, then you do outperform the autoaggressive and the mask case as well. Um, yeah. Anyway, so yeah, it's a flow matching recipe. I hopefully that sort of kind of made sense. Again, there's a little bit of the art involved in the sense that we need to create the conditional velocity that generates a single data point. That's the main thing. As long as we have that, then all we need to do is do a conditional expectation with some Bregman divergence, and we're done, right? So, given some data, the main thing is that path design. We don't explicitly design the path. That's the thing we don't want to design the probability path first. We don't have to, right? It tends to restrict ourselves if we do. Anyway, so yeah, so if you're interested, we do have this code released on GitHub. You can try playing around with it. We have ImageNet training and also discrete text training on this fine web data sets. And we have all 3 different versions for continuous Euclidean, Riemannian, and also discrete supported here. Not all the features are supported, but it's a code base you can already get started with if you're interested. Anyway, that's it for the talk. Let me know if you guys have any questions.
Thank you very much. Questions? Oh, yes.
Can you hear me from here?
I can hear you, yeah.
Okay. Thank you very much for the talk. It's very fascinating. I have a question about continuous flow matching. So in continuous flow matching, we had time as kind of a dummy variable for matching the distributions. What about in cases or applications where time is part of the domain, like video or audio? How do we handle that?
So one naive way that people like that we've done audio and also video is to just treat the entire thing as like we don't align the dummy variable time with the actual time. So the entire thing is the thing we generate. It's going to be like a 3D convolution or some sort of architecture that generates that, right? Images will be like height by width by hidden depth, and then for video it would just be height by width by temporal you know, number of temporal blocks frames by depth. And then we can still do transformer and whatever architecture on there. That's one way, is to just treat the entire thing as a single data point. Other approaches for doing video generation are to combine it with an autoregressive model, because they tend to make sense to do autoregressive in the frames from oldest to the newest. And so they combine autoregressive models with flow matching, and each stage the flow matching sort of, I mean, there's a lot of different ways of combining it. You can take a look at a paper called pyramidal flow matching, which I quite like, but they sort of have different resolutions for the flow matching model that's sort of incrementally getting upsampled as you go along. But yeah, so the different ways of handling this, and I think there's going to be even more interesting ways of handling this in the future. But for now, those are the two main approaches, which is just treat the entire block as a data point, or you do autoregression on the temporal axes.
Yes.
Hey Ricky, thank you for this talk. Very, very insightful. And I just have a question for the discrete flow matching compared with the autoregressive training. Do you have any comments on the training efficiency of like training a text generation model with discrete flow matching versus autoregressive?
Yeah.
algorithm?
So yeah, that's a great point. So the pretty good. Okay. Actually, sorry, I'll just keep it at this slide. Yeah, so the autoregressive model is much more efficient because currently, because you don't directly sample some xt, right? So when we think about the flow case, even if we do only insert only like decode the unmask the rightmost variable, we still need to sample some xt, and then we learn some loss for doing it. But autoregressive models directly just learn all the conditional distributions because you only have one particular ordering. And the current way that we do the mask diffusion, I believe does not have the same training efficiency, but there are ways to get around it, and it's not entirely clear that we cannot beat or obtain the same training efficiency just yet. But currently, yeah, as you might think, that's definitely one of the biggest bottlenecks of training non-autoregressive models, just because we have to like sample some XT, and now we have a bunch of noisy data points. Maybe some of them are masked out now, and so the model only sees a portion of the sequence, and it tries to predict the rest. But there's no way of like trying to overlap a lot of a bunch of different t values. Because it's not a causal attention architecture anymore. Did that make sense? There was also a paper called Sigma GPT, which I do like, which is so to me, I really don't like the mask corruption, just because I say it's not training efficient, but also because it's basically the same thing as an any order autoregressive model. It's just the ordering is random. But there's a nice paper called Sigma GPT, which basically just treats it as any other autoregressive model, and then you can use a causal attention architecture. You get KV caching and things like that. But I do think there is hope for fixing the non-autoregressive models as well. Just yeah.
Oh yeah.
I'm kind of not really advanced in math, so is there a way to describe how when you do generative video like that, like the one where you had I think it was a koala bear on the surfboard? Is it picking up video, I mean matching video for, there was originally a guy on that surfboard and somehow they were able to superimpose the koala bear over the face of the body of the person or something? I mean, is that kind of what it's doing, but it's doing it mathematically? I may sound like a noob here, but
I think it's doing it more magically than mathematically. I don't know how it's doing it. I don't think anyone knows. But the training recipe literally is what I showed you in one slide. Like this is the code. It's just more complicated with the neural network, but this is literally the code they used to train that model.
wow.
And they just have a lot of data. So this is for text and image, text and video pairs, and they just have a lot of data that they trained this on. Somehow the model is generalizing. I think this is the nice thing that we've been sort of seeing there's sort of like a compositionality effect happening, like for image to text, text to image models and now text to video models. In the sense that, as you might imagine, there's sort of a lot of different objects happening here, and you use the word transpose, and there's different ways of composing these things. I think also a lot of it is in the text embedding model as well, right? There's typically a text encoder that learns that given the text or tries to compose what each component should look like, and that's getting fed to the general model for the video. So I think the compositionality, I would put more like I'll give the most of the credit to the text encoder, but for sure the generative model is the one that sort of somehow is able to take a lot of this data and be able to still generate crisp videos, at scale.
You make it sounded easier than surfing. I learned to surf. It was more difficult than generative.
I'm sure there's a lot of details in there that I'm not aware of either.
Other questions?
I have one quick question. So thank you for the amazing talk. Just one question is, when you train flow matching on ImageNet, I was curious about the training time. How long did it take for you to get the result?
Yeah, for us, I think on 256, we generally train for about a week. We use one node, so that's 8 GPUs. But like I think we also don't really we haven't really tried training faster. I think the model tends to converge very, very fast. It's just if you really want to eke out the last bit of performance, you want to train for longer. That tends to be maybe one of the things about this sort of noisy loss as well. This is true for also like diffusion models. I think maybe also why flow models work a little bit better. The second loss here is very, very noisy. The first loss is very easy, right? It's just regression. The optimal is 0, but we don't have this loss. The second one, what tends to happen in practice is the loss just like we get almost no signal from seeing the loss decrease over time, but the model is improving for sure. It's just extremely, extremely noisy. So it benefits a lot from training for a very long time to get the final performance as well.
Thank you so much.
Ricky, I have a last question probably. So what's the major difference between the discrete probability case and the continuous case? Because I feel that there should be some differences there. I mean, I kind of get a feeling the discrete case should be harder. So do you encounter anything that's in line with this or disprove this? I kind of feel that discrete case should be harder.
Yeah, no, I think the discrete one is harder just because there's no metric that we can use. Like on continuous space for images, we sort of have this idea that like similar pixel values are very similar to each other, and we don't really care, right, about getting exact pixel value. But on discrete, it's such a large space, this token space, right, 100,000 spaces. But then we cannot put it on a real line, right? We cannot put it on some sort of, we have some embedding, but still have very high dimensions. But in general, I just think it's a very large space, but it doesn't have a way to easily traverse that space. And this is why we have the mask construction working so well, because the mask is like treating every single token value equally, and they're only going to the mask token. There's no like complicated graph that we're traversing where each node is a token value. I think ideally that's what we're trying to get at maybe with this sort of work, where maybe we want to have a more complicated graph and build a continuous time process on the graph itself. It's just jumping from node to node. But no, if you actually want work at scale, the thing that works best is this graph is extremely sparse, and they're all connected to the single max token, and they're connected back. And that's it. They're not connected to each other. That's the mask case.
Yeah, I mean the intuition I get is that because the continuous case, your vector field, because you can move anywhere in the space, right? In the continuous case, so you can have a relatively smooth vector field. But if we think about discrete case, because we can only move to discrete point. So I think the vector field, if we are able to define a vector field in any sense, I think the vector field tends to be more zigzag, right?
Mhm. Yep.
And that makes the learning harder, right? From that perspective, because you're learning a predictor that's predicting the vector field. Now, it's like this function is a very complicated function in the discrete case, right? Because it can change dramatically just because the space puts a lot of constraint on which direction it can move.
Exactly. Yeah. I think that's what I was trying to get is like there's a sense of
Another way of saying the same thing you're talking about, but that we can get why it's harder.
yeah, there's a sense of locality in the container space, right? But for discrete, we have to create our neighbors.
Right.
Um,
Okay. Thank you very much, Ricky. Have a nice day.
yeah, thank you so much, guys. Thank you so much. Bye bye.